Myself, Dr. K. Viswanath Allamraju, Institute of Aeronautical Engineering, Department of Mechanical Engineering, Dundigal, Hyderabad. We are going to discuss today about the bending stresses in beams. In this bending stresses of beams, bending stresses of beams are related to the module 4. So the course outcome and Bloom's taxonomy is the course outcome of this module 4 is apply the knowledge of theories of failure, shear force and bending moment relations for analyzing flexural stresses, shear stress distributions and failure of beam sections. And the Bloom's taxonomy related for this module 4 is apply. Here, what is the concept of pure bending? So here, we know, as we are aware of the fact of internal reactions developed on any cross section of beam may consist of a normal force, a resultant shear force and a resultant couple. Now in here we are going to study only bending stresses investigations. So we are going to restrain the twisting and buckling loading conditions or effects of twisting and bucklings. So what we are going to do here, that we are going to put a constraint on the loading such that the resultant normal and the resultant shear forces we are going to consider as 0 on any cross section perpendicular to the longitudinal axis of the member. That means the shear force equal to 0, and that means dm by dx, the rate of change of moment, that is known as the shear force, that equal to 0. That means the m remains constant. That means the change of moment with respect to x, dm by dx, is nothing but the shear force that is going to 0. That means no changing in moment dm. That means m remains constant. Now here, the stresses in beams, if we consider this figure consists of the pure bending. This pure bending figure relates to the pure bending concept. It is a overhanging beam. The point loads are acting at point C and point D at the free ends, and the support reaction, the reactions at A and B are RA and RB. It is nothing but equal to the weight which is actually acting downwards, vertically downwards, that RA equal to W and RB equal to W. So this weight is acting from the left hand support A with a distance of small a, and the load which is acting is capital W, and the right hand side at the free end from the right hand support capital B, and at a distance of small letter a, and the load vertically downwards is acting as W. So after calculating the vertical reactions and drawing the shear force diagram, the shear force is observed as negative at the left side between C and A, and is the point, and it is positive between point B and D. This is the positive zone, and here it is negative zone shear force. But the shear force is 0 between the points A and B. Is completely 0. No effect of shear force. Now, after drawing the bending moment diagram, it is observed that linearly varying between from C to A up to the magnitude of WA, and similarly from B to D, it is varying linearly from D to B, and B is the maximum WA, and between A and B the W remains constant. This WA remains a constant, that is bending moment diagram is constant. Here that means for this beam the shear force between A and B is 0, but the stresses set up in the length of the beam are known as the bending stresses. So the length of the beam under constant bending moment, the length of the beam, that is A and B, between A and B, it is experiencing the constant bending moment. So this phenomenon, this concept is said to be under pure bending. So this is the concept of the pure bending. So but though the loads are acting vertically downwards, that point at the point C and point D, W and W, but after it is observed that the shear force is 0 between A and B. That means no effect of shear force. There is no effect of shear force between A and B. So the shear force, it is completely free from shear force effect between the distance A and B. Whereas A and C, it is a constant, that is the value of the shear force is W, and between B and D, the shear force is W, but it is a positive shear force. So, but between A and C, it is the negative, and between B and D, it is the positive shear force. But A and B, the distance between A and B, the shear force is 0. But shear force 0, but bending moment remains constant. That this bending moment is constant, okay, this is said to be, that means this beam is said to be under pure bending. Under pure bending. When the beam is bending, before deformation, if you observe the lines to understand better the concept of pure bending, these are the horizontal lines and vertical lines. Before deformation, all are straight lines. Straight lines, horizontal straight lines and vertical straight lines is the before deformation. After deformation, if you observe in this figure, after deforming, this is the beam. Before deformation is the straight lines, horizontal lines. So after deforming, either upwards or downwards, the vertical lines remains straight, but it may be under rotation mode. But whereas the horizontal lines becomes curved, the horizontal lines you can observe, it is under curve. These are the curved lines. Become horizontal, becomes curved lines. So, but the experience, the beam experiences here in this portion at the top, compressive stresses. Compressive stresses, and the outside layer experiences tensile stress. Tensile stresses. Here, that means upwards portion, here this portion is under compression and bottom portion is under tension. So there is an axis. This axis is known as the neutral axis. So whereas on a neutral axis passing through the neutral surface, so this neutral surface has no change in length. Neutral surface experiences neither compression nor tension. So neutral axis is the line of intersection. Line of intersection of neutral surface in a transverse section is the surface. The neutral axis passes through it. The surface horizontal. The line of intersection of neutral surface with the transverse section is known as neutral axis. So that all the sections, all cross sections remains plane and perpendicular to the longitudinal axis after deformation. Before deformation is same and after deformation also same. So there are certain assumptions in order to prove pure bending theory or simple bending theory or flexural theory. So the assumptions are here: the material of the beam is homogeneous and isotropic. That means it is the same composition and constant E, that means modulus of velocity in all directions. I mean the directions are X, Y and Z directions. And Young's modulus of the material is constant before in compression and tension. There is no change. Why? Because it's the material property. The property of the material is remains same. And the transverse section which are plane before bending remains plane before bending and after bending. There is no effect. The transverse section of the transverse section which are plane, which is plane before bending and after bending. Now another assumption we are going to we made here, it is beam is initially straight and all longitudinal filaments bend in circular arcs. That's what beam bending, the circular arcs. And the radius of curvature is large compared with the dimensions of cross sections. And one more thing is that each layer of the beam is free to expand and contract. So these are the certain assumptions are there to prove, that means in order to derive the bending theory, simple bending theory. So what is the preamble for this? So here the normal stresses due to bending are known as the flexural stresses. Flexural stresses, that's why it is known as simple bending theory or flexural theory or theory of flexural. For what type of beams? For straight beams we are going to study. So here the preamble is that when a beam is having an arbitrary cross section is subjected to transverse loads, the beam will bend. When the beam is subjected to a transverse loads, what is the transverse load here? Suppose it is the beam. When the load is acting transverse load, these are the supports, then it causes to bend. So causes to bend, that's why the beam will bend when it is subjected to transverse load. When it is subjected to transverse load, it will bend. Two ends are fixed. To apply the load in transverse direction, it bends. So here one more thing is that in addition to the bending, when the beam is subject to transverse load, not only bending takes place, another one is called twisting and buckling also may occur. The twisting and buckling occurs, but here in order to investigate the effect of bending, so we neglect the twisting and buckling becomes. So what we are going to do here, the simultaneously takes place. Not only bending, twisting also takes place and buckling also. These three combinations are complicated to solve. So for simplification, going to neglect or constrain the twisting and buckling and consider only bending. Now, that's why here we are interested to investigate only bending effects alone, not other effects. So that constraints are, that means the constraints are neglecting, buckling and twisting. Now here there is a beam we considered. The beam is having a cross section and the planes here E, F, G, H, and the layers are the neutral axis layer is a CD, and the plane, that is the neutral surface, the axis is the neutral axis. And there is a layer we considered at a distance y. That layer is the AB is the layer. When we apply the couples, bending couples, that is M, the moments, it causes bending. That is the bend inwards. So the beam experiences inward layers are under compression and outside layers are under tension. So here the layers, the curvature, layers of curvature, it becomes the radius of curvature becomes R about the neutral axis, that is A dash, B dash. Now about that is the C dash, D dash is radius of curvature is C, which is making the bending angle is making an angle of theta. So before bending and after bending, we are going to consider that there will be strain will be developed. The strain developed here, it is The strain here it is that the strain in fiber AB, that is change in length by original length. The change in length, that means initially it is AB, after curvature that is A dash B dash, that is A dash B dash minus AB, that is the change in length, by actual length is AB. Now the strain in fiber AB, it is A dash B dash minus AB by AB. But before it is AB equal to CD, it is the same. But and also after that AB becomes C dash D dash, because the radius of curvature is larger enough such a way that the dimensions of the cross section in comparison to the dimensions of the cross section. Now here A dash B dash minus C dash D dash by C dash D dash, that is the strain. The strain A dash B dash, what is A dash B dash? R plus the distance, R plus Y times theta, substitute here, and C dash D dash, it is neutral axis, so that is R theta. So this is R plus Y times theta minus R theta by R theta. So R theta get cancelled, it becomes Y by R. Is what? So that is the strain. The strain, another definition from modulus of elasticity, that is Young's modulus of elasticity equal to stress by strain. From this strain equal to sigma by E. This is also Y by R, this is sigma by E, equation 1. Equate 1 and 2, then Y by R equal to sigma by E, or sigma by Y equal to E by R. This is one of the equation. And after finding out this is the relation, now one more is that here when there is a bending, there is a moment of inertia takes place over the cross section of the beam. So let's assume that about Y, this is the point we are considering the layer, at this layer at a distance Y, and the thin layer we are going to consider, that is a dy. Now what is the area? That is we want the force, that is if the shaded area, this is the strip dA, then the force on the strip, when it is bending, there is a force acts on the layer. That force equal to sigma times area, force equal to stress into area. What is the stress? That is sigma into dA. What is the sigma here from the equation before? That is E by R into Y, and dA, E by R into Y into dA. This Y dA, okay, that is now moment we have applied here. What is the moment equal to? Force into Y, distance. The force is E by R into Y dA, and the distance is the Y. Then if you multiply E by R into Y square dA, the total, for total layers if you consider, that is total, the total moment if you want, then it is the sigma times Y square dA. Sigma times Y square dA, that is E by R into sigma times Y square dA. Y square dA is nothing but mass moment of inertia. So then the equation M equal to E by R into sigma times Y square dA is nothing but mass moment of inertia, or that is I. Then from that M by I equal to E by R. Now this is one of the equation. We know before that sigma by Y equal to E by R. So this is also E by R, this equate. Then finally the equation is obtained as sigma by Y equal to M by I equal to E by R. So now here this sigma times Y square dA is the moment of inertia, that is area moment of inertia, that is the property of the material, that is called moment of area, that is moment of second moment of area, that is known as moment of inertia, area moment of inertia. So this equation is known as the bending theory equation or flexural theory equation. Here we did not consider the effect of shear force, the effect of shear and buckling. So that's why twisting and buckling are not considered. That's why there is no term related to shear stress here, related to shear force, that is the tau. It didn't appear. So here from this equation Here from this equation, that the assumption of, what is the assumption we assumed here? Pure bending. We considered only pure bending. There is no shear force being present. That's why it is known as pure bending equation. Not only simple bending equation or bending theory equation, it is pure bending equation. So this equation, one more thing, equation gives the stresses, the distribution of stresses which are normal to the cross section. Okay, this equation gives distribution of the stresses which are normal to the cross section. Which are normal to cross section. What is that meaning here? In x direction. Suppose the area of cross section is here. Consider the beam. If you cut it in vertical direction, along this section, how the stress varies in x direction. The stress may be varies like that. In x direction, variation of the stress in x direction, okay, normal to the cross section. Here if we consider this is the cross section, how the variation of the stresses takes place. So this equation, the unit for sigma units is the normal stress, that is in Newton per meter square. Y is the distance from neutral axis to the referential area, that is in millimeters or meters. Next, m is the moment, that is Newton meter. I is the moment of inertia. Units for moment of inertia is meter per 4. E is the modulus of elasticity, that is Newton per meter square. R is the radius of curvature in meters, that is sigma by y equal to m over I equal to E by R. This is a simple bending equation. Now here one more thing is that there are certain interpretations we can make the equation which we derived here. Now here one more thing, that is the equation which we have derived, sigma by y equal to m by I equal to E by R. Now here sigma by y, you can equate from this equation to equation, that is sigma by y equal to m by I. From this equation we can calculate sigma after knowing the 3 knowns and 1 unknown, that is m by I into y. Next, if we equate sigma by y and E by R term, sigma by y equal to E by R. Now sigma equal to E by R into y. Now if we want to going to check the dimensional homogeneity, the sigma units are Newton per meter square, and units for m by I into y. M units is Newton meter, it is meter for 4 and it is meters. So cancel mm's, then the dimensional homogeneity Newton per meter square. So dimensional homogeneity maintained here. Whereas coming to this sigma Newton per meter square on the left side, on the right side Newton per meter square for E units, Y unit is meter and R units are meters. Meter get cancelled, then it is again same dimensional homogeneity we checked here. That means we can calculate sigma stress value from this formula, that is m by I into y, and also the stress also can be calculated if we know the modulus of elasticity and radius of curvature and the y values. So based on the data, given data, we are going to use this formula, that is sigma equal to m by I into y. Similarly, sigma equal to E by R into y. Now in this manner, we are going to study the calculate the stresses value. Here one more thing I would like to discuss, that here the sigma by y equal to m over I equal to y by E by R. Here this I is the area moment of inertia. I is area moment of inertia. There are two types of inertia. One is mass moment of inertia, another one is area moment of inertia. The moment of inertia here in this theory of bending equation, this area moment of inertia. If there is a section having depth d and width b, how to find out what is the moment of inertia about x-axis? Ixx equal to bd cube by 12. And if you want about y-axis, Iyy equal to db cube by 12. According to perpendicular axis theorem, if you want about z-axis, Izz equal to Ixx plus Iyy, that is bd cube by 12 plus db cube by 12. In that, if we common bd, if you common it, bd, if you make it common, d square plus b square by 12. This is for rectangular section. If area of moment of inertia for square cross section, about x-axis and about y-axis, as we have know that for rectangular cross section Ixx equal to bd cube by 12. For this square, make it d equal to b, then d into d cube by 12, that is d power 4 by 12. And similarly about y-axis also it remains same, d power 4 by 12. That means the moment of inertia about x-axis equal to the moment of inertia about y-axis, that equal to d power 4 by 12 for the cross section of square cross section. Here the cross section is rectangular cross section. And if you want about z-axis, Izz equal to Ixx plus Iyy, then that equal to d power 4 by 12 plus d power 4 by 12. That means 2 times d power 4 by 12. That means d power 4 by 6. So about z-axis, it is d power 4 by 6. About x-axis and y-axis, the area moment of inertia is d power 4 by 12. Units for area moment of inertia, as I mentioned in before slide also, it is meter over 4 or millimeter power 4 or centimeter power 4. Now, this is for rectangular and square cross sections moment of inertia. The moment of inertia of a circular cross section or circular lamina. For circular lamina, moment of inertia, that is, the diameter is d. D is diameter. Then it becomes pi d power 4 by 64. About x-axis or y-axis, also pi d power 4 by 64. So this is a moment of inertia. About z-axis if you want, then according to perpendicular axis theorem, Ixx plus Iyy, that means 2 times pi d power 4 by 64. That means pi d for 4 by 32. Or that IZZ equal to IXX by 2. So 2 times IXS, IZZ equal to 2 times IXX or 2 times IYY. So it is pi d for 4, 2 times pi d for 4 is 64. That is pi d for 4 by 32. So these are the concepts of area, moment of inertias of different cross sections, that is rectangle, square and circular cross section. And here the references we followed in this session, these are the reference textbooks and websites which were mentioned here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.